All right, let's jump right into this explainer and uncover the hidden mechanics of how enterprise security actually tracks everything happening inside a Linux system. Look, if you spend any time around servers or cloud infrastructure, you already know the real battleground for cybersecurity isn't sitting on someone's desktop. It is buried deep inside the Linux operating system. So today, we're going to explore exactly how modern security operation centers and those advanced endpoint detection and response tools manage to monitor this vast, complex landscape 24/7. I mean, you probably type PS, aux, or top into your terminal all the time, right? But have you ever paused and wondered how the system, or a modern EDR for that matter, genuinely knows who is running what? And more importantly, how on earth does it know if a seemingly normal process is secretly a hacker operating in the shadows? It's so easy to just look at a terminal output and take it for granted, but the underlying mechanics here are absolutely fascinating. So, we're going to peel back the onion today. Here is our agenda. 1. Everything is a process. 2. Unmasking malicious behavior. 3. The truth in system calls. 4. Evolution of kernel monitoring. 5. Containers are just processes. And 6. The AI security era. Let's kick things off with Section 1. Everything is a process, the core of Linux architecture. This is the foundational rule that governs absolutely everything running on a Linux machine. Now, you might be familiar with a famous Unix philosophy that everything is a file, but the crucial point here is that when it comes to taking action, everything, and I mean literally everything, is a process. Your Nginx web server? That's a process. Your database? Process. Your SSH session? Process. Even a Docker container running microservices, or some hidden Python script acting as a malicious Trojan, they all fundamentally operate as a process inside Linux. And here is what happens under the hood. It's basically a very specific protocol. When you run a command, whether you're just opening bash or accidentally executing malware, the Linux kernel rapidly steps in. First, it establishes a unique PID or process ID. Then it allocates the necessary memory. Third, it creates the process context. And finally, it allocates file descriptors so the process can actually read and write data. It's only after all this is done that the kernel hands it over to the scheduler, and the process is officially born. But here's the incredible illusion we all fall for. Standard commands like ps, top, or htop, they don't magically scan the system like some high-tech radar. They actually just read plain text from a virtual file system called proc. You see, the Linux kernel dynamically creates a folder in proc for every running PID. So when you use those everyday tools, you are quite literally just reading files out of a directory. It's a beautifully simple design, but from a security perspective, it has a massive flaw. Which brings us right to Section 2, Unmasking Malicious Behavior, Existence versus Actions. Because our standard tools just read folder lists, we run into a huge problem. Hackers can easily manipulate those lists. A totally normal Nginx web server and a renamed hacker Trojan might look absolutely identical in the terminal. Think about it. A hacker can just take their malware, rename the file to ./nginx, and run it. To your PSX command, it looks exactly like a web server. No red flags. This is exactly why SOC and EDR tools don't care about a name. They care about behavior. True monitoring isn't asking, does a process exist? It's asking, what is this process actually doing? So instead of relying on easily spoofed names, defenders track specific, undeniable behavioral indicators. First, they look at process creation and PPID, basically who started whom. If a supposed web server spawns a bash shell, which then spawns Python, which opens Netcat to create a reverse shell, well, that's highly suspicious. Second, they monitor file access. Is that web server suddenly trying to read your etsy/shadow password file or access your private SSH keys? And third, network connections. Is a random Python script suddenly initiating an outbound connection to an unknown IP address on port 4444? Because that is classic command and control beacon behavior. Let's dive deeper with Section 3, the truth in system calls, the ultimate choke point. To actually catch this malicious behavior, we have to drop down to the lowest level of the system, the place where lies simply cannot be told. Every single process, no matter how stealthy or heavily disguised it is, eventually has to ask the Linux kernel for permission to interact with the hardware or the system. It does this via a system call. If malware wants to open a file, it must use the open syscall. If it wants to execute a new program, it uses execv. To create a network connection, it calls connect. Because system calls are the absolute choke point between user space and the kernel, they are practically impossible to hide, and this is exactly what top-tier EDRs are watching. Moving right along to Section 4, Evolution of Kernel Monitoring, the High-Level Zone. Because system calls are the ultimate source of truth, the history of cybersecurity is basically the history of figuring out how to watch them efficiently, and we've evolved a lot over the years. The oldest method is ptrace, which is what tools like strace use to hook a process's system calls. But honestly, it's very slow, drags down system performance, and is easily detected by hackers, so it's pretty rare for modern EDRs to rely on it alone. Then we got AuditDeed, the official Linux auditing system. You can think of it kind of like an airplane's black box, recording executions and file access. It's solid, but can be a bit rigid. Finally, we arrive at the modern king of monitoring, eBPF. The absolutely crucial point to understand here is that modern advanced EDRs, tools from heavy hitters like CrowdStrike, Cilium, Tetragon, and Falco, rely heavily on eBPF. eBPF is revolutionary. It allows us to run sandboxed programs directly inside the operating system kernel. It hooks into the Linux kernel right at the system call level with almost zero performance impact. When a user process makes a system call, the eBPF hook catches it instantly, analyzes it, and sends it straight to the EDR engine for behavioral analysis before the system even blinks. It's a total game changer. All right, Section 5, Containers are just processes, busting the paradigm. Before we look at how AI handles all this eBPF data, we need to quickly bust a major misconception. A lot of people out there think Docker containers are basically miniature virtual machines running their own isolated, heavy operating systems. I need to be totally clear about this. They absolutely are not. A container is actually just a normal Linux process. Literally, that's it. It's simply a process that has been isolated using standard Linux kernel features called namespaces and cgroups. Namespaces limit what the process can see, and cgroups limit what resources the process can use. It creates this brilliant illusion of an isolated machine. And honestly, this perfectly illustrates exactly why a container escape vulnerability is so terrifyingly deadly. If a hacker breaks out of that isolated namespace, they aren't escaping into some hypervisor layer. No, they drop straight down onto the host machine as a standard, often highly privileged host process. And that brings us to our final stop, Section 6, the AI security era, replacing human eyes. Okay, so we have eBPF perfectly extracting every single kernel-level action. But the sheer volume of this data, it's astronomical. It is way, way too much for any human analyst to watch, like drinking from a fire hose. This brings us to an incredibly powerful and frankly a little terrifying future. We are now combining the omniscient kernel visibility of eBPF with artificial intelligence. Instead of a human staring bleary-eyed at logs, we have AI engines continuously and instantly analyzing process trees, syscall patterns, network flows, and user behavior in real time. And the AI isn't just looking for a hash of a known bad file anymore. It's actively hunting for complex anomalies. Autonomous threat hunting. It learns what your specific baseline looks like. It knows exactly how your database normally behaves or what a typical SSH session does. So it instantly flags a weird bash execution or a Python script that suddenly starts behaving like a network scanner or an SSH session that attempts lateral movement across the network. It spots the weirdness the millisecond it happens. Ultimately, what you should really take away from this explainer is that the entire paradigm of system monitoring has completely shifted. The modern cybersecurity battlefield isn't asking, is there a virus file on this disk? It is asking, in real time, hundreds of thousands of times a second, does this process act like a hacker? It is a massive shift from identifying malicious existence to analyzing malicious intent. Which leaves us with an absolutely fascinating puzzle to chew on for next time. If our modern tools like eBPF can see absolutely every system call, and our AI can analyze behavior instantly, how are the world's best hackers still managing to evade detection? How do you hide a process when the kernel itself is watching everything you do? Think about that, and we'll unpack the secrets of Linux process evasion in our next explainer. Catch you then.